Okay, so this is the roadmap for this particular chapter. First, we are going to start with basic requirements of memory management. That is, as an OS, what we are supposed to do, right? What we need to fulfill to have efficient memory management, and what are the functionalities, right, that you have to consider as a part of the umbrella of memory management, right? Then comes partitioning methods, right? As we are all aware, uh, how many processes we should ideally support in main memory. The number is not defined, right? But it should be more than one, right? In main memory, we would like to have more than one ready processes. Yes or no? Because if you don't have multiple ready processes, right? Suppose you are having 10 processes at present, and one of them is the ready process out of that. Rest 9 are blocked. Right? Is that an efficient situation from memory management perspective? Out of 10, only one is currently ready, others are blocked, right? No. So ideally what we want, the basic goal of memory management is we have to divide the memory in such a way that we can support as many processes as possible, right? And as many processes should be able to be loaded in main memory. Okay, so the loading part and decision part, right? When to load that process, right? That is going to be answered by memory management. But which process to load? Who answers that? Which component of your study that you have done till this part? Yes, it is scheduler. And which type of scheduler is that? When to load a process in main memory? What is that type of scheduler? Okay, am I audible once again? We had an interruption due to network got disconnected. Okay, okay, thank you. Fine, so let us just resume. Okay, so that is the second part, right? So I was asking about the type of scheduler that decides when to load a process in main memory. Options are long term, short term, medium term. Which is that decision? Medium term is related with swapping, right? You swap a process out, you bring that process in, right? That happens at medium, you can say, occurrence, right? Short term is you are already there in main memory and you bring that process in execution. So from ready queue to running state, from ready to running, that is short term. So the only option that is left is, as Yash and Preet has answered, it is long term scheduling, right? Because long term scheduling decides, yes, General, that's correct, right? Long term scheduling decides when to bring in a process in main memory. Okay, so are you clear? Those who have answered as medium or short term, right? Okay, so this is just a revision, right? Because that is what is required as we go along. Fine. So memory partitioning is a method by which we divide the memory efficiently so that we can have as many processes as possible in main memory, right? So you have a better choice, right? Even when most of the processes are blocked, right? You will have one option at least to choose from, right? So that is how we should divide the memory. There are many methods of this. We'll see that in detail. Then comes paging and segmentation, right? So it is actually a part of partitioning only, right? So in paging, we try to divide the process into small size components, small size parts, while segments are larger size components. We'll see that in detail, right? So these many topics we'll be covering in next 3 to 4 classes, right? Most probably within this week, we'll be finishing up to segmentation. Right? That is the goal. Okay. So we have seen the example of uni-programming system, right? Uni-programming means you are having one process present, right? While what is multi-programming? You can support multiple processes to reside in main memory at the same time. But does multi-programming mean that you can dispatch multiple processes? Does multi-programming mean that you can dispatch multiple processes for execution? No, right? Because if you have a single CPU, then you can dispatch only one process at a time, right? Yes, it is interleaving, right? Interleaving will happen, right? But if you have multi-programming and multi-processing both, then what is the answer? We can dispatch, yes, right? That is the answer, okay? So if we assume a uni-programming system, most basic system, right? Then your memory can be divided in two parts, right? One part of the main memory is always occupied by the OS, right? We either call it as a resident monitor or we call it as a kernel, right? If you remember, we had studied about that batch operating system, right? Batch operating system has a concept of monitor, right? Monitors was nothing but it was a part of your OS, right? That was loaded in main memory and it was controlling the dispatching of the processes, right? Later on, monitor got a new name. It was named as a kernel, but kernel is a much more complex entity than monitor, right? So can we just refresh what is kernel? Can anyone write down the basic definition of kernel? What is kernel? It is a subset of functions, but which functions, right? That is what you need to answer. I hope you have not forgotten those concepts, right? If you want to talk with kernel, you require system call interface, right? So system call, we can invoke the kernel functionalities, right? That is what we have seen, right? So what is kernel? It is most frequently executed functions of the OS, right? That is the non-technical definition, basically, right? It is a collection of functions, but which functions of OS? It is most frequently executed. So if you think about memory management functions, can you say they are going to be executed frequently? Memory management functions, yes, right? Dispatching functions or dispatching related functions, yes, again, right? File management functions, answer is again yes, right? So these are the core functionalities, right? Those functions are packaged together and they are called kernel, okay? So does not matter that what part of your OS is residing, your OS is going to be divided, fine? One part of the OS is called the kernel, right? And kernel always resides in main memory, okay? So you need to assume that your available memory is total minus kernel. Is that clear, right? Your main memory available is total available minus the space required for the kernel, right? So the remaining space is occupied by the program, right? And we call that program as a process, right? Because when it is executing, the program converts to the process, right? This is for uni-programming. What about multi-programming? In this case, in case of uni-programming, the task is very simple because you just have one process to choose from, right? And what about memory management logic? Or what is the complexity of memory management logic in this case? It is easy or complex if you want to write memory management logic for uni-programming system. It is very easy, right? Because you just need to find out what is total memory, right? You need to find out what is the memory occupied by kernel, right? Subtract that, right? And whatever remains, that is going to be the memory available for your program. Okay, so partitioning and management both are easy, but when the problem arises, when you want to support or when you want to load multiple processes in main memory, right? That is what is multi-programming. Yes, right. So in a multi-programming system, user part of the memory, right? Now, what is user part? It is the part except kernel, right? It is the part except kernel, right? Total minus kernel, that is your user part. Okay, that must be further subdivided. Yes, occupied by processes. That's correct, right? To accommodate multiple processes, right? So we need to subdivide because now we are supposed to provide multiple processes and their storage, right? And that is where the memory management becomes complex, right? So memory management is vital in case of multi-programming system. Do you agree with this statement? If it is a uni-programming system, we actually don't require any management, right? We don't require any code that is supposed to manage because we are just supporting one process, right? But as the number of processes increase, the complexity of memory management increases, right? So this is defined or justified over here. If only a few processes are in main memory, then for much of the time, all the processes will be waiting for IO, right? And CPU will be idle. Are you clear with this up to this? Right? If you have less processes, right? Yes, I'll repeat. Suppose you are having two processes only. Few is equal to 2, for example, right? And both of them are IO bound processes. I hope you remember that concept, right? IO bound and CPU bound, right? What is the difference? IO bound versus CPU bound? Okay, sorry for another interruption. It seems that internet is getting disconnected periodically. Am I audible once again? Okay, okay, fine. Let us continue. Okay. So we were discussing regarding if you have only two processes, right, in main memory, and both of them are IO bound, what will happen in worst case? Both of them will be waiting, right? And when both of them are waiting, right, what is the CPU's situation? It is idle. Is that clear, Rishi? Are you clear with this, right? So what is recommended ideally? We are looking at a problem right now. What is the solution? The solution is memory management should be capable enough to provide continuous supply of ready processes, right? Or at least you should have multiple processes reside in main memory. Are you clear with the solution also? Right? So that is what is the problem, and this is the solution, right? So what OS has to do? OS has to keep track of the available processes, right? If all the processes are blocked, which are currently available, what is the only solution we can do? Even though I'm supporting 15 processes, what if all 15 are blocked? What is the solution for that? Yes, we have seen that in basic process chapter. Yes, if you want to have a solution, what do you think? Swapping, right? We can do swapping, isn't it? Sure, sure. If all 15 processes are blocked at present, CPU is idle. Okay. So what you will think as a solution to come out of this situation? We can do swapping, right? I can swap 2 or 3 processes out, and I can bring a new process, or at least a ready suspended process. Remember that state? Ready suspend. The process is ready, but it is lying where? In secondary memory, right? So the only solution that memory management can do is it has to do swapping. Yes or no? Right? So memory management is very complex task because it has to keep track. That is the first thing. And after keeping track, if any issue arises, it has to find out the solution. Getting this point, right? I'm trying to explain you the complexity of memory management unit that is a part of your OS, right? It is a very, very critical component, right? Okay, and can the process size grow or shrink? Yes, definitely, Vishruth. Because if a process requests more memory, right, it has to be allocated if that process deserves. And by deserves, what I mean is it might be of high priority or it is a critical process. Yes. So definitely, if you want to grow or shrink, or let us say if you want to just grow, then also you might require to do swapping. Yes or no? Because what if extra space is not available at present, right? So you have to shift out any of the existing process to provide more space. That is another issue, right? We are going to see all these problems and their solutions, right? That is the goal of this memory management chapter, right? Okay. What is the need of memory management, right? As the memory is cheaper, right, and it is continuously getting cheaper, right, as the days are passing, even the you can say the sizes of RAM are increasing, right, day by day. When you buy a new laptop or a new machine, you are getting more and more RAM, right? If you buy after 2 years, you will be getting the newer version in less price, right? But with that getting cheaper, what is going to increase? Size of application, right? So it is a trade-off, right? Memory is getting cheaper, so we are getting more memory at low cost, but in the same time, the app sizes are increasing, right? So what we need to maintain a balance is we should be able to accommodate or provide the same performance, right? Even though the app size increases. Yes or no? We should be able to provide the same performance as we were getting earlier, right? Okay. With existing memory capacity, right? Because see, you can't buy a laptop every year, right? So people have to think in this manner also. That is, if the application size is getting doubled every month, right? The laptop RAM or even the hard disk will run out of space even in a year, right? So that is not possible. That is not a practical solution, right? So that is why Whose task becomes complex? It is the memory management designer's task, right? You have to make your existing algorithms as efficient as possible. Are you getting my point, right? So that is why memory management is a crucial area, right, in part of the OS. Okay. Another requirement for memory management is a swapping, right? As I said, we require to continuously swap in, swap out a process, right? Even in case of virtual memory, we will see that, okay, how trade-off, because in era of 2 GB RAM, we had apps consuming 1.3 GB and now 16 GB. Yes, so why it is balanced? That is the point I was trying to make. Why it is balanced? Because it is the OS which is continuously being optimized. And OS is managing this space. That is why you are seeing no difference, right? Even you had, even I have used a 256 MB of RAM, right, earlier. That machine was running fine without any problem, right? Why? Because memory management was capable to handle multiple applications even on 256 MB of RAM. And nowadays, if you have 32 GB, then also applications are running fine, right? Although the sizes have increased, right? Is that fine, Rishi? So we are maintaining a balance by optimizing the memory management capacity or algorithms, right? That is the essence. Okay, fine. Another challenge that we have is IO is slow, right, as compared to CPU. Even you take SSD, right? SSD is much faster, but that is again, you can say a hardware device, right? It is not still going to match with your CPU. Agreed? Right? Speed of SSD is much better than your hard drive or even your RAM, but still, it is not going to match up with the CPU because CPU have been continuously optimized, right? So even in current scenario, we require efficient time management or efficient decisions have to be taken by the memory management unit, right? So what is the goal? OS has to cleverly time the swapping, right? So when to swap, that is again a question, right? Because if you keep on swapping from time to time, let us say if I set a period, after every 5 minutes, I will see which processes are blocked, right? Let us think about that situation. And if two processes are blocked at that point, I will swap out those two processes. Is that the efficient approach? Setting a time? No, right? Because what if you just swap out that process, right? And then dispatcher actually has to dispatch that next because your current process is having dependency on that process. So what you have to do? You just swapped out that process, and now it has to be brought back in. So we are having two penalties, right? First we swapped out, but now it was required, so we have to bring it in, right? So you will be wasting time, yes, right? So when to swap and how to swap, both are the memory management decisions, right? So that is why we need memory management. I'll again refresh the concept. As swapping is a difficult job, right? And IO is slow compared to CPU. That is why we need to have optimized memory management logic, right? Okay. So the bottom line of all this concept is this, right? Memory needs to be allocated to ensure a reasonable supply of ready processes, right? Now, we are not saying a number over here because it depends upon the situation, right? How many processes you can support at a time, that depends upon priority also, right? But we say that a reasonable supply of ready processes to consume available processor time. So what is the best case for memory management? The best case can be if you are having 10 processes in main memory, all 10 are in ready state. Are you getting the point? If you are having 10 processes in main memory, if all 10 are in ready state, you are having the best case. Why? Because even after you dispatch the first one, and it is an IO bound process, it will block. But you have 9 options to choose from, right? Because still remaining 9 are in ready state, right? What is the worst case? All 10 block after running for short time. You have a short burst. For every process, you have a short burst and they are blocked, right? What is the only solution to come out of this situation? As I discussed earlier, swapping, right? That is the only solution. So process concepts, process state concepts, and swapping concepts, right, are required to study this chapter. Right? So that's why I'm taking time today to just revise that. Okay, fine. Let us now focus on requirements, or these are also called functions of memory management, right? So if you think, or if you are writing the SRS of OS, right, and if you are writing memory management module, let us say your requirement R4 is memory management, these 5 will be sub requirements. Are you able to map that, right? So basically, if you want to implement memory management module in your system, these 5 things have to be implemented. That's why they are called requirements of memory management or functions of memory management, right? Let us understand each one of them by the name, and then we will go in detail. First is relocation, right? I'll give you a simple example. Suppose you are loading process P1 for the first time, right? You are loading process P1 for the first time, and it is getting swept out due to some reason. Okay. Now, when P1 is brought back inside, once again, is it guaranteed that it will get the same location? Yes. What is the answer? Should I repeat the question? If you are having process P1 currently running, it is getting swept out or it is getting suspended due to some of the reason, right? Now, again, when P1 is brought back, right, will it be assigned the same memory location in the RAM where it was allocated? There is very less chance of this, right? So what happens in this situation? This method is called relocation. Your process continuously relocates itself depending upon the current availability, right? But what is the challenge when we are having relocation of process? You all are writing the MFP programs, right? You are writing the address as 60H. Suppose this condition is satisfied, move to 60H location, right? That is written in the program. But what will happen when you relocate your process to some other location? That reference has to change or not? Can you modify in the program? Tell me, can you modify the program? Program cannot be modified, right? Because it is written. So what has to be managed? Mapping. Are you following this? Right? OS has to take care that earlier when you were referring to 60H, the actual location was, let us say, 500, right? And now after the process is brought back once again, the location is, let us say, 7,000. Okay. So that mapping has to be managed, and this is known as relocate. Yes, that is correct, Rishi. It is address mapping, right? Relocation and addressing, these are related concepts. We'll see that. Is this basic clear? Relocation, the name itself tells you the idea. What does that mean? Relocate the process. Okay, is there a need for a parallel space in order to store location? Yes, so if you want to have, then it is possible, right, Harsh? You can maintain the parallel space, but that is not possible for every system, right? Yes, means some array is allocated to have allocated another new location. Okay, so basically, suppose you are having current position for a process P1 is pi to 50, right? The range of the address, let us say, for example, is 5 to 50, right? In the first reference. And when you load it again, it becomes, let us say, 650 to 700. I'm giving some random addresses, right? Okay. So in this case, yes, you have to maintain the track by some means, Vishruth, right? Either it is array or any other method, but track has to be maintained. Getting the point? Right? Okay. So relocation and addressing, These two topics are combined over here. Next comes protection. Now, as we discussed in the first lecture, right? Whenever we are having OS, normal users should not be able to access the area of the OS. In other words, can we allow user programs to access the kernel without having privileges? Obviously not, right? So that is a protection requirement, right? Protection has also been has to be managed by again OS, right? That is another task of the OS, right? But can OS itself manage on its own, or it requires the support of CPU or your hardware for protection? What do you think? Can OS on its own manage the protection requirement, or it is the task for OS plus CPU hardware? What do you say? Yes? Both. Okay. Good that I got one answer. What about others? Try to answer. OS plus hardware. OS. Okay. The question is protection requirement be satisfiable by only OS, or OS requires the hardware support also? Right? Okay. If you say only OS, right, then the problem that you might face is, right, OS has to keep track of every address allocation. Yes or no? Right? And if you let OS maintain that task, right, the important task or important things might be missed out. Right? So actually this is a combination. OS manages, or you can say OS is just an administrator in this task. Right? Who actually manages protection? It is the CPU. Right? Because who knows the addresses? OS or CPU? It is CPU. Right? I am answering the question in the other way. Who knows the addresses? It is not the OS, it is the CPU, because CPU generates the addresses, right? So who is the best person to manage the address protection? Are you getting the answer now? The best person who can manage the protection of memory is CPU, right? But that has to be managed, isn't it? Someone has to control that, right? So OS acts as an administrator, right? But actually, who is going to do the job? It is your CPU or your hardware. Okay. So the final answer is protection can be satisfied with combined effort of OS and the CPU hardware. OS has rights to manage addresses. Yes, so that's what I'm saying. OS plays a role over here, right? But who does the background task for protecting, or who is going to set the locks actually? It is the CPU hardware. Getting it? Okay, I'll repeat once again. Yes, how it is done, we'll see, right? We are going to see all these things in detail, right? So basically, memory has to be protected. Is that first point clear? Right? Memory is known, or memory is allocated by which entity? It is generated by CPU, right? Or it is allocated by the CPU. But who is going to keep track of that allocation? It is OS, right? So now, keeping track and allocation, both things have to be combined for protection. Yes or no? Keeping track and protection, or you can say allocation, both things have to be combined. And that is why the answer is OS plus hardware. Got it? Right? Because one entity, either OS or CPU hardware, cannot achieve both the things. That is why we are going with a combined approach. What about relocation? Relocation will be managed by which entity? OS or hardware? Or combine again? Think about that, right? We will answer that later on. Okay. Next is sharing, right? See, we have seen producer-consumer problem. We are also going to see reader-writer problem tomorrow in the lab, right? So, whenever you are sharing something, is memory management going to play a part over there? Yes, right? Because that data structure, which is holding your information, where it is located? That buffer which you are using in producer consumer, it is located inside the memory, right? So that is managed by the memory management unit, right? Directly. Okay, so sharing is again a requirement of memory management, right? Suppose you are having one process, right, or let us say one program, right? Now, can the same program code be shared by two or more processes? Yes or no? Same program code can be shared by two or more processes? Yes. See, for an example, you are using Microsoft Word, right? If you are having an MS Word application, although you are creating two different files, right? But still, are we using the same MS Word program? Although we are creating two files parallelly, but can we say that I am referring to the same MS Word program? Yes, program is same, but the interface at the outer level, you are having two files open. Okay, so sharing is a good option. What is the benefit of sharing? When you are sharing the same code across two or more processes, what is the benefit? You are saving memory, isn't it? Because if sharing was not available, then you have to copy the same MS Word code multiple times, right? And what is going to be occupied? Ultimately, when you are creating multiple copies, your main memory space gets occupied, right? So efficiency decreases following this, right? So that is why sharing is a very, very important thing, right? Okay. Next comes logical organization, right? So this is pointing to the same example which I discussed. Your program, or you can say nowadays we are writing object-oriented program, right? So object-oriented programs are written in which manner? They are modular, right? They are modular in nature. But how the actual memory is designed? Is the memory designed in a modular manner or it is sequential? It is sequential, right? So there comes a question. If your program is written in a modular manner, right? And if the memory addresses are linear, what we require? What we require? Mapping, isn't it? I have to map the segmented program, or you can say the modular program, on the sequential memory locations, right? And how to manage that efficiently? That is again a task of OS, or that is again a task of memory management. Clear? This is called logical. Why? Because program is containing, let us say, modules. Modules are logical, right? But physically, the memory is allocated in which manner? Sequentially, right? So that mapping has to be managed. Okay. Last one, physical organization, right? Physical organization means how the memory is actually divided in types, right? Now, in normal scenario, we have only two types of memory, right? Main memory and secondary memory, right? So this last requirement states that how OS efficiently manages the mapping between the main memory and secondary memory. That is how you efficiently manage the swap in, swap out operations, right? That is why it is called physical. Physical means you are having the hardware. That means your RAM and hard disk. Okay. When the information is being transferred from one location to the other, it has to be done efficiently, right? Okay, so I'll repeat all of them once again, then we will look at the detailed slides. Okay, relocation means what? When you shift a process to some other location, right, the addresses will have to be updated, right? So you need to have a mapping. Okay, what is protection? Protection means if you want to protect a certain area of main memory, right, hardware also plays a role over that. It is not only the job of OS, right? We have answered that question. Fine. When you are sharing a common data structure, or when you are sharing a common part of the code, right, memory management has to keep track how the sharing is happening. Okay, what is logical organization? You are having program in modular manner, right, and the memory is allocated sequentially. So how that mapping occurs, that is the task of logical. Physical is talking about types of memory, right, and swapping. Okay, let us go in detail now. So main memory is shared by multiple processes, as I said, and programmer does not know where the program will be placed, right? Okay, and when it is swapped out, and when it returns, it may be into the different location. Understood this? Right? This is called relocation. And when relocation happens, what has to be done? Memory references must be translated every time when relocation happens. Because in program, you are writing static addresses. They have to be mapped, right, at runtime. Okay? That is called relocation. If you want to achieve relocation, what has to be done? Addressing, right? If you want to achieve relocation, addressing has to be done, right? So what is addressing? If you remember what this figure is saying, this is nothing but a process image, right? This is nothing but a process image. Remember, process image contains PCB, program, data, and stack, right? Suppose you are jumping from this location to this location, right? And in program, you written that statically. But when relocation happens, what has to be done? Suppose this location is, let us say, 600 when the process is first loaded, right? Now, when it is loaded once again, this location is now changed to 6000, right? So, do I need to change the, do I need to update the addresses accordingly? If my location of process changes, the addresses have to be updated, isn't it? Right? So, if you want to achieve relocation, addressing has to be properly done, or you can say address mapping has to be properly done, right? Same applies to data, right? Suppose your program is referring to a certain data that is located over here. Now, when relocation happens, this position may change. This actual address may change, right? So again, you have to do a mapping. Okay. How all this happens, we will see that in detail. Right? We are going to see the algorithms and everything, right? Okay. So that is covered over here. When OS loads a process, right? It knows the address of PCB, it knows the address of program area and stack area, right? But what mapping has to be done? We have to map between the actual program references, that means what is written in the program, right? And the physical location, right? Suppose in program you have written 60H, but when you are allocating that memory, where that 60H position is located. Are you following this? Right? So that mapping and conversion has to be done. Who does that? Again, CPU, hardware, and OS both. Why only OS can't do this? I'll just take 2 more minutes, right? Then we'll stop. Yes, why OS alone cannot do it? Because we have to do memory allocation, and wherever memory allocation and tracking is there, hardware is required or CPU is required. Okay, fine. Protection. As I said, whenever a user process, right, wants to access kernel, it cannot directly access that, right? So we require a protection of kernel, right? That is the first thing. Okay. Another thing is, by mistake, your program should not branch into the area of another process. Can we allow that? Can we allow branching from one process to the other? If you allow that, the complexity of the, you can say, memory management further increases, right? And even what if the data structure pointers are violated, right? So that is why we generally don't allow. Okay, so we are required to provide 2-level protection. First is what? We should prevent access to kernel. That is the first thing. Second thing is we should prevent access to other process area, right? So you should stay within bounds. That is what is necessary. Okay, fine. Let us just look at this statement, then I'll stop. Satisfaction of relocation requirement increases the difficulty of protection. Yes or no? Just answer that, then I'll stop. Whenever you are relocating, right? Let us say when the process was first loaded, right? It was between, as I said, 5 to 50, and you set a lock on that location, right? When the process is swapped back in, the address is like this: 650 and 700. So do I need to lock this region now, 650 to 700, which was locked earlier? Yes, right? So as many times you perform relocation, your locks have to be released and locks have to be reset. Yes or no? Right? So that is why this statement is true. Fine. Okay, so I'm stopping over here. We'll continue in the next class, right? Because it is already 10:44. Okay, thank you.